Okay, so now again, just to look back at where we've been and where we're headed, is we took a look at first the CRD, the completely randomized design, one-way ANOVA, polynomial fits, and so forth. I think probably this week, by this point, we've talked about linear contrasts at least a little bit, but we'll continue to talk about linear contrasts, which are really just linear combinations of our treatment effects. Now we're going to talk about getting the whole big picture explanation of our model and how the treatment effects should be interpreted by using something called multiple testing. Now, for even more advanced theory-based students, you may not have heard much or seen much of this. Maybe you've seen the Bonferroni test, a few things here and there. However, this is actually a really important area within statistical analysis, and for those working with applied research scientists in the big fields, you need to know this stuff. In fact, when I go to, this happens to be my focus in statistical methodology research, and when I go to the multiple comparison procedure conferences, guess who the big sponsors are? They're areas that use statistics for discovery research, such as biomedical fields, big pharma. If you look at our programs at these conferences, you see Amgen, Merck, Johnson & Johnson, and so forth. The big pharma companies are sponsoring this work. Why? Because they have a vested interest in knowing that their results are valid, are reliable, and that they're not missing or over-reporting effects that are spurious in any way. Okay, so there's whole sets of research areas that are very focused on, say, pharmacological research, where we talk about primary effects, secondary effects. We won't get into all of that complexity in this course. You'll learn the basics of multiple testing. So let's think first. I think by this time you've had your kind of rationale activity to convince you that multiple testing is useful, but this will be a little bit more of that convincing. I like to do convincing that you need to do this. Suppose you have a 20-sided die. 19 of the sides are labeled 0 and one side's labeled 1. You roll the die 1. What's the chance of getting a 1? Well, that's an easy question. It's only 5%, right? 1 out of 20. Now you roll the die 2 times. What's the chance of getting at least 1? 1. Okay, well, that's 1 minus the probability of getting 2 zeros, because at least 1, 1 means you get 1 in the first, 1 in the second, or 1 for both the first and the second. So that would be 1 minus the probability of 0, both rolls. And so that's 1 minus 0.95, the probability of 0. And it's not both. I was doing both in my head, but it's to the 20. But if we were talking about 2 rolls, we'd have a 2 right there. But we're talking about 20 rolls, so the probability of getting a 0 in all 20 rolls is 0.95 quantity exponentiated to the 20th power. And when we subtract that from 1, we get 0.642. So our chance of getting at least 1 1 in 20 rolls is actually about 64%. Then if we do that 100 times, so we simply replace this 20 with 100 here, it's almost for sure, 99.4% of the time, we're going to get at least 1 roll that's a 1. So think of this 1 as an error. Okay, our significance level is much of the time 5%. So if we have a significance level per interval estimator of 5%, let's say, then if we do 20 interval estimators, we can expect that 64% of the time we're going to have at least 1 error. And we're not saying 1 error, but at least 1. If we have 100 interval estimators we report as a result of the study, we are for sure almost going to report errors. So how do we control this preponderance of errors? because we can see how likely it is that we will report spurious results if we don't use multiple testing control in reporting our experimental results. Doing a 5% level test when the null is true is like rolling the die. You have a 5% of rejecting the null, just like one roll of the die. And then Gary's going back through what we just talked about. So the essence of the multiple testing problem is here at the bottom. How do you control error rates when you do a lot of tests? Whoop. We use this in class. I like this cartoon. I think it's kind of shows why multiple testing is needed. I think studies that don't use them should be thought of as pilot studies only and not conclusive. It really weakens your experimental results when you don't make use of a multiple testing procedure. Things are even worse if you just do a bunch of tests and you kind of snoop the data to look for something interesting. That's not to say I don't do this from time to time. I'll be honest here. Sometimes I do that, but I make sure then I have it grounded in some theory by the time I publish results. In this case, your chance of rejecting the null is going to be really high when you're data snooping. It takes, and he crosses out, heavy blunt instrument with powerful procedure to keep error rates under control. So we don't want it to be too heavy and blunt. We want something powerful, okay? That's what we're going to shoot for. Because now we're going to get a little bit into the theory behind multiple testing. We have several null hypotheses. Let's say we're going to do K simultaneous interval estimators, or K-tests as a result of our model that we're summarizing. So we have H0 H0 on up to H0K. Then we define H0 to be the intersection of all of these null hypotheses. Okay, so it's our global null hypothesis that all of the individual K null hypotheses are true. So this would be saying, that there are no effects. None of our linear contrasts are significantly different than 0. Could be one way to state in a very wordy way our global null. Now let's assign epsilon I to be the type 1 error rate for the ith test. So we'd have epsilon I for I equal 1, I equal 2, on up to I equal k. And epsilon is going to be our type 1 error rate for the combined null, that overall H0. When we say error here, we're talking about mistakes, okay? That should be obvious by now. So declaring a true null to be false is a type 1 error. This is a false positive, where we're essentially saying there's some effect, when in fact there is not an effect. Failing to reject your false null is a type 2 error. This is a false negative, saying something's not happening when in fact something is happening. Gary makes the comment, he says, in ye old days, one would say accept the null. I've never said that. I guess he is older than I, so maybe they used to say that. But we do say reject a false null, okay? And that's the case of a type 2 error. One of these is a more costly error to make than others, okay? So a type 1 error or a type 2 error, you've all had basic stats 101, so you know that we tend to focus on type 1 error, and that's our level of significance. Whatever we set that as controls our type 1 error, and we will continue to do the same thing here. But if you think about it, this is a most of the time important effect. Like if we're talking about drug efficacy, if we make a type 1 error, we're declaring something to be null, a true null to be false, okay? So we're saying that the drug, which in fact is not efficacious, is in fact efficacious. That could cost a drug company millions of dollars if you make that kind of mistake. So in most cases, we do want to do this. However, when we start talking about secondary effects, type 2 errors become more costly because that is all about missing effects that are important secondary outcomes of, say, taking a medication, the so-called side effects. Here's a nice table format. You've seen this before, I am sure. This is not new. Study this on your own. Our general approach, like I said, is to control the probability of type 1 error. Here's our notation, though, and this I want you to pay a little bit more attention to. Notice that for K hypotheses, we can say that A plus B plus C plus D equals K. That's just summing up. Every single one of our tests will fall into one of these four camps. We will fail to reject, and in fact, that null is correct, so A is a good decision, D is a good decision, B and C are mistakes, so to say. In practice, we don't know these counts, but we know that they sum up to K. That's all that we know. So we can talk about the per comparison error rate. The per comparison error rate just ignores multiple testing, which is what a lot of people do, even though some of us don't like it. So here you just do a separate test for each null hypothesis, ignoring that any other tests even exist in this universe, okay? So you're saying, here's the probability of rejecting the null hypothesis for the ith test, provided the experimental assumption that the null hypothesis is true. And we just say, let's control that to be less than epsilon, that probability. In effect, then, we're going to have K different tables with different counts for each of those A, B, C, and D counts, frequencies. And because we assume that all nulls are true, B and D are both going to be equal to 0 for all tables or sub-hypotheses. So what we're really testing is C bigger than 0? Remind ourselves real quick what C is. C is that probability of rejecting the null hypothesis when in fact the null is correct. So that, remember, is a type 1 error when we do testing. And so we're really just saying, let's control that CI probability bigger than 0 under the assumption that the null hypothesis is true to be less than epsilon. Versus, so if we remember here, we're talking about the per comparison right there. So we could talk about per experiment. So if we control the per experiment error rate, we're controlling the probability that any null hypothesis associated with an ith contrast or test is rejected, thus rejecting the global H0. When all the H0 i's, hence H0, the global test H0, are true. So then our per experiment error control reads like this. Reject any H0 I provided or assuming H0, the global, is true. And that gets compared to the per experiment error rate of epsilon. Again, this works because we have all nulls true, so B equals D equals 0, and the per comparison error rate could be written like this. So we want C for the whole set of hypotheses or tests to be bigger than 0, provided H0 global is true. And that, again, is bounded by epsilon, that probability. We could also talk about false discovery rate. So remember here, we're just talking about the probability that we get at least one false rejection of the null hypothesis. That's what C bigger than 0 means. But we could talk about a different kind of mistake. So here's something that has just a little bit of a different perspective on the same phenomenon. The false discovery rate allows for the possibility that some H0 I are actually in reality not conforming to the null hypothesis, but are true. And this is a very valid assumption to make. I'm looking at the time here and I'm realizing I need to pause the video for a moment. So we're going to start with false discovery rate for our second part of our video about multiple testing.